Okay, let's take a look at some sample tests from the AP College Board here. It's the non-calculative section. First one, you can see here that they've got the limit as h goes to 0 of this function. You should recognize right away that this is the derivative. So the function is the cosine of x, let's say. So the derivative of that is a negative sine of x. And looking at these two values here, you know that you're trying to evaluate this derivative at 3 pi over 2. So what is the sine of 3 pi over 2? Well, you should have that pretty much memorized. But if you need to make yourself a handy chart, unit circle works great on this one. That's pi over 2, 0, pi, 3 pi over 2. That's what we're looking for right there. So those coordinate points are 0 and negative 1. And since sine is all about y, the answer is a negative 1. But because you have that minus sign out in front of there, the answer is positive 1. So be careful there. Number 2, I give you a graph and they list 5 points, and they want to know when is the derivative and the second derivative negative. Alright, so this question's asking us, do we know what the first derivative means? When the first derivative is less than 0, the function is decreasing. When the second derivative is less than 0, it's concave down. Okay, so see, it's concave up here, concave down, so it's either A or B. Well, B, you can tell it's decreasing right here. That derivative is negative, right? So the answer is B. Alright, moving right along. Slope of the tangent line to the curve. Here you got to do implicit differentiation and then solve for dy dx, and then plug in the points. X is 2 and y is 1. Be careful right here. We have two product rules basically working together, right? And you're adding them together. So just recall that f prime g plus f g prime. So we're going to take the derivative of y cubed is 3y squared. Don't touch the second one. And since we just took the derivative of y, we need to write dy dx plus the first times the derivative of the second, which is just 1. And then on to the second one. The derivative of y squared is 2y. Don't touch the second one. Dy dx plus, don't touch that one, and the derivative of x squared is 2x. And the derivative of 6 is 0. So we're going to keep this one on the left, this one on the left. We're going to move a positive y cubed and a positive 2y squared x over to the right. So we have a negative y cubed minus 2y squared x. And of course you don't have to show all these steps on a multiple choice, but just for explanation purposes. So what's left? This and this are gone, right? So let's factor out a dy dx, and you get 3y squared x plus this 2y x squared, and then we're going to divide it by that. So dy dx is equal to a negative y cubed minus 2y squared x all over 3y squared x plus 2y x squared. And then we're going to go plug in our x is 2 and our y is 1. Let me switch colors here. So we have negative 1 cubed minus 2 times 1 squared times x, which is 2, and that takes care of the numerator. And in the denominator we have 3 times 1 squared times x, which is 2, plus 2y. So we have 2 times 1 times x squared, which is 4. So we'll do it over here. We have a negative 1 on top. 2 times 1 is 2, times another 2 is 4. So we have a negative 5 on top. Looks like it's going to be C. Now let's take care of the bottom just to make sure. We have 3 times 1 squared is 3, times 2 is 6, and then 2 times 1 times 4 is 8. So indeed it is that. Alright, so just make sure you don't make an arithmetic mistake on that, and you should be in good shape. Alright, number 4. Let me make this just a little bit bigger if I can. Okay, we have a volume problem here, right? The volume says y equals 2x and y equals 2x squared between 0 and 1. So we don't have to figure out if they intersect or anything like that. We just need to know that we're going to evaluate from 0 to 1. And we're going to rotate this about the line y equals 3. So maybe just a real quick sketch over here. So 1, 2, 3. We're going to rotate it about this line. And let's see, we have 2x and 2x squared. So we're only going from 0 to 1. So plug in a 1, you get 2. So a straight line goes right here. Let me erase this. Let me draw this a little bit more distinct. And let's not use yellow. Alright. And then we'll make the quadratic, we'll make the square function green. You plug in 1, you get 1 squared is 1, times 2 is 2, so the 2 intersect here. You do need to know which one's on top and which one's on bottom. If you're not sure, you plug in a small value, say 1/2. 1/2 squared is 1/4. So in between at 1/2, it's going to equal what? 1/2 also, right? And if you plug in 2 times 1/2, you get 1. So the linear function is above the quadratic. So it looks sort of like this, and the parabola is underneath. So our axis of rotation is not the x-axis. Since we're rotating about that line, the curve furthest away from that blue line is the green line, right? This distance is 3, right? And if we're rotating this green line, it's going to be 3 minus this square function. So it's 3 minus 2x squared. And remember, area is pi r squared, but volume is pi r squared times the h, right? And the h is going to be our dx. So we have to square our radius. That's the top curve, and the bottom curve is the linear function. So it's still 3 is the rotation axis. So another way of thinking about this is the radius, right? So to get that radius, it's 3 minus the red one. So it's 3 minus 2x squared, and all those quantities. Put our pi out in front, and that's our volume. So, looks like it's going to be answer choice A. Be careful because B, they don't square this value. They switch the places, right? So make sure you're understanding which one's on top and which one's on bottom. Okay, let's take a look at number 5. Number 5 as a function x to the fourth minus 2x cubed, and they want the answer choices have to do with relative extrema, so minimums and maximums. I see points of inflections in here, so we should probably take the first derivative and look for our extrema. So we have 4x to the third minus 6x squared. Might as well crank out the second one too. That's 12x squared minus 12x. And I think I want to do the second derivative first. Kind of go out of order. I'm going to factor out a 12x, and I'm going to get x minus 1. And that's the second derivative. So what are our critical points, which tell us our possible points of inflection? Because that's what they're asking us about. You can see points of inflection here, 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 and here. So set it equal to 0. Well, this portion, when x equals 0, the whole thing goes to 0. And in this little section, when x equals 1, so we have two possible points of inflection. Now we know it's 0 there. So if this thing switches signs, we know, or switches concavity, then we know that it's a point of inflection. So let's just pick a value over here, say -1. I'll do it up here. So we put in a -1, 12 times -1, that quantity is going to be negative. -1 minus 1 is negative also. So we have a negative times a negative to give us a positive, right? Okay. And let's pick a small number like, say, 1/2. Well, if you put in a half, you get 6. That's clearly positive. And if you plug in 1/2 take away 1 is a -1/2. So here, it looks like we have a point of inflection right there. It switches from concave up to concave down. And then let's go pick another value out here. Pick a large value like 2 or 3. We get a positive 24. 2 minus 1 is positive. So positive times positive is positive. So it looks like we have 2 points of inflection. And so we can eliminate B, I suppose. And let's go ahead and analyze this one. We have to see if it has 1 relative extrema or 2 or 3, I suppose. What's factorable here? We can take out a 2 and x squared. Leaves us with 2x minus 3. So there's really only 2 points. So I guess we could get rid of this one. 2 possible points of relative minimums or maximums. When x equals 0 and when x equals 1.5 or 3/2, right? Set that equal to 0 and solve, you get 3/2. So just once again, pick an easy value here. Say a -1. -1 squared is positive. So we get positive there. And a -1 here would be -2 minus 3 is negative. So on this side it's negative. Okay, so pick a nice easy number between 0 and 1.5. No, like 1 would be a great candidate. Plug in a 1 here, you get positive. You plug in a 1 here, you get 2. 2 times 1 is 2, minus 3 is negative. So here we have a decreasing function, another decreasing function here, so we don't have to worry about that. In fact, it's a point of inflection. And let's go look at a value larger than 1.5, say like 2. Once again, 2 squared is 4, 4 times 2 is 8, clearly positive. Plug in a 2, 2 times this 2 is 4, 4 minus 3 is positive, so we have positive times positive, and this indicates that we have a what? A relative minimum. So there's only one relative extremis, so it looks like C is the good answer. Alright, moving right along. They want us to find the derivative and evaluate it at 0. Just a quick pointer. Remember that square, when it's like that, it indicates that the entire quantity of sine is squared. So this is a chain rule. The big picture is we're taking the derivative of something to the second power. So 2 times sine of 3 minus x to the first power, right? Which we normally don't write. And then we have to go look on the inside of this, and we see that we have a sine of some angle. So we have another chain rule here. So let's do this one in blue. So the derivative of sine is cosine of 3 minus x. Alright, so we're just basically undoing layer by layer. And now we're going to take the derivative of 3 minus x, which is negative 1. So, looking at this, we have a negative 1 times 2, so we have negative 2. Now, we can go ahead and plug in our 0. So we have the sine of 3 minus 0, which we don't know how to evaluate, and the cosine of 3. So, looks like it's going to be A. Alright. Okay. Here we have a differential equation. They give you the derivative, and you basically are trying to solve the equation. So this is a nice problem. We can just cross multiply here. And let's see if I can make this a little bit bigger. Okay. So cross multiply, and we get y times dy is equal to 4x dx. So now we're going to integrate both sides, and we'll put our constant over here on the right. So the derivative of y is y squared over 2, and that's equal to 4x squared over 2 plus our constant. Okay. No reason to clean this up any further right now, I don't think. We have an initial condition of x is 2 and y is a negative 2. So plug in negative 2 for y, square it, divide it by 2, and we could simplify this to 2 over 1x squared. So 2 times 2 squared plus c. Alright, and this becomes what? That's a positive 4 over 2, so we have a positive 2 equals, that's 4, 4 times 2 is 8, plus c, so it looks like our constant is equal to a negative 6. Alright, so let's go ahead and fill it in. We simplified this to what? 2x squared minus 6. Solving for y, we're going to have to double everything, multiply everything by 2. So we get y squared is equal to 4x squared minus 12. And take the square root. Alright, so if we take the square root, of course we have a positive and a negative answer, right? But they want us to just solve it in this one case, right? So which one of these do we need to pick if the answer is negative 2? clearly we just need to look at the negative answer. So let's see, where would that would give us, looks like C. And when x is greater than the square root of 3, well, we don't need to concern ourselves with this since that's the only answer choice, but the reason that's true is the inside of the square root has to remain positive. So if you say that 4x squared minus 12 has to be greater than or equal to 0, I don't know why they didn't include, well, anyway, so you solve for that and you get the square root of 3. Okay, let's move on. What is the average rate of change? Alright, remember in our study of calculus we first started talking about the average rate of change, and we sort of made a connection that this is sort of an algebra technique, and the instantaneous rate of change, or the IROC, is sort of our calculus where we take the derivative, right? So the rate of change is just basically the slope of the secant lines that connect between these 2 points, 0 and 3. So this is basically Algebra 1, 8th grade stuff. Delta x over delta y, if you will, dy dx. So we have to find the function value at 3. So the function value at 3 would be 3 to the 4th power is 81. 3 times 3 times 3. Minus 5 times 3 is 15. So what is that? Let's just write that down. So we have, and then the second, when we evaluate it at 0, plug in 0 there, you get 0, right? So 80 minus 15 is 65. So it looks like we have 66 over 3, and reduces to 22. There we are. Okay, another motion problem here, position. And they want to know for what values is the speed of the particle increasing. So when you see the word speed, you want to think absolute value of velocity. Another way of evaluating this is a trick we talked about, where if the sign of the velocity matches the sign of the acceleration, we say that a particle is speeding up, right? So one way to do this is to do a sign analysis on the first derivative. This is a PVA problem, right? They're giving us the position, take the derivative to velocity, take the derivative of velocity to get acceleration, and we'll evaluate it. Alright, so the first derivative is velocity, and I'll just be explicit here. So the derivative of position, that would equal what? 6t squared minus 48t plus 90. And before we move on, let's go ahead and factor out a 6. Looks like everything can be divided by 6. So should make our life a little easier. It's minus 8t, and 15, or 90 divided by 6 is 15. So over here we have what? T minus 5, T minus 3. So the critical values are T equals 3 and T equals 5. And that's velocity. Let's see, let's go ahead and evaluate this since we got it all set up. Of course, 6 out here is not going to affect anything. So pick a value, let's pick a value like 1. If we put a 1 in here, we get 1 minus 5 is negative. 1 minus 3 is a negative 2, so we have a negative times a negative, we get positive. 0 at 3, correct? So choose a number like 4. 4 minus 5 is negative still, and 4 minus 3 is positive. So the particle's moving to the right between 0 and 3, and it's moving to the left between 3 and 5. And let's go see what happens over here when it's bigger than 5. So pick 6 or 7, it doesn't matter. Let's do 6. 6 minus 5 is positive. 6 minus 3 is positive. So it changes directions and starts heading back towards the right here. Okay, so this doesn't tell us whether it's speeding up or not. We have to look at the acceleration. So we'll go back to our velocity, take the derivative of that to give us our acceleration. I suppose we could take the derivative right here. Let's switch colors. So we have constant 6, we have 2t minus 8, and that goes to 0. So the only critical value here is setting this equal to 0, we get t is equal to 4 seconds. So I like to draw my number line and match it up so that I can really get a good look at it. So all I have to do is look at a number smaller than 4, so let's just pick 3. 3 times 2 is 6. 6 minus 8 is negative, so it's negative here, right? It's negative even at 3. Maybe draw a dotted line here. It's still negative until you get to 4. So you can see here that between 3 and 4 seconds, it's negative, so particle's speeding up there. So let's go ahead and pick a number bigger than 4, like 5. 5 times 2 would be 10. 10 minus 8 is positive, so it turns positive here, right? So there's my 4. So between 4 and 5, acceleration is positive and the velocity is negative, so it's not speeding up there. But once it hits 5, they both match up, right? They're positive in both sections here. So we're looking for an answer that has when time is greater than 5. No. Yeah, greater than 5 and between 3 and 4. Between 3 and 4. So something like this. Alright. Looks like E might be the answer choice, so hope you're able to follow along with that explanation. Alright, number 10. When you first look at this problem, you may think U substitution, but U substituting won't get us very far. So the easiest way to solve this one is to rewrite it. And I always suggest doing that if you get stuck. So now you can basically distribute. I just rewrote x to the 1/2. You distribute that, you add the exponents, so 1 plus 1/2. So we have x to the 3/2, and then we have negative square root of x. And now we're taking the integral of this, right? So you can basically split this up into 2 parts since we're adding or subtracting. So add 1 to 3/2 and you get 5/2 over 5/2 minus add 1/2, add 1 to 1/2, you get 3/2 over 3/2. Well, that 2 comes up in front, so you have 2/5 x to the 5/2 minus, and that 2 comes up to the top, you get 2/3 x to the 3/2 plus our constant, don't forget that. Alright, so not too bad once you saw the trick of simplifying this or rewriting it. Alright, I already worked that one, I guess. Limit as x approaches infinity. This tells us the horizontal asymptotes, but it's not asking us about that, but it's good to keep that in mind. So the shortcut on this is to look at the highest exponent value. Looks like square is highest in the top and highest in the bottom. So this is a Bobo Batu. It's actually a Betsy problem, right? So when the bottom equals the top, it's the ratio of the coefficients. So we have a 1 coefficient on top and a -4 here on bottom. So hope you can zip through that one pretty quick without even writing anything down probably. Okay. Alright. Let me erase my work here. Alright. We have an area problem. It says, let's see if we can make this a little bit bigger for you. It says, what is the area of the shaded region? So we have 5x minus x squared. So the top curve is the excuse me, is the 5x minus x squared. So we know that's going to be our top curve. And subtracting off the bottom curve, or this linear equation, minus 2x. And we got to find the limits where we want to integrate from. We know we're going to start off at 0. So now we just need to fill in this value right here. So, and once we get that, we can actually clean this up before we take the integral, right? We're not squaring this function. It's not a volume problem. It's just an area problem. So let's just set these two equal to 0 over here. We'll do it in blue. So we have 5x minus x squared equals 2x. Where does it equal 2x? That's the question. If we subtract 2x and subtract 2x here, we get that 3x minus x squared is equal to 0. Factor out an x, you get 3 minus x. So we get our one intersection, which we already saw on the graph, x equals 0 and x equals 3. So it looks like this is at 3. You don't even need to worry about the y value, but it is 6, I believe, yeah? Alright, so we're just going to plug in the x limit, and 5 minus 2 will give us 3x minus x squared from 0 to 3. And this is what? 3x squared over 2 minus x cubed over 3. And we're going to look at it from 0 to 3. Of course, the 0 is going to end up being minus 0. Plugging into 3, we get 9 times 3, we get 27 halves. And 3 cubed is 27. 27 divided by 3 is 9. Common denominator would be 2. So you get 18 over 2. And that equals 9 halves. Okay. Let's go on to the next one. Alright. This is a bit of a tricky problem here. Let's look at the question here first. They give us that y is equal to this weird function 5 plus some value here, right? And in this section over here, looks like maybe we're going to use the second fundamental theorem of calculus. Although that's not an x, it's 2x. We can use the chain rule if we have to use the second fundamental theorem of calculus, and I think we are. Because look at all the answer choices. They all have the derivative, right? All the way through. So let's take the derivative. That'll eliminate some of the answers. So if we take the derivative of both sides, we're taking the derivative of the right side too, right? D over dx. So the derivative of 5 would be 0. And the derivative of this is just what? E to the minus t squared. So we're going to plug in our 2x. But since we don't just have an x here, we have to use the chain rule. So what's the derivative of 2x? Just simply 2, right? And if you square this 2x squared, you get the minus stays there. Minus 4x squared. We can put the 2 out in front. So it looks like only the last two are possible answer choices. So, you know, we've got it down to 50-50, right? Well, let's take a look at it a little bit closer. And what exactly does this mean if I plug in 0 for x? Let's plug it into the limits of integration. Maybe that'll get us somewhere. So we have 5, and we have 2, and 2 times 0 of e to the negative t squared. Well, we can't really evaluate this integral because that's t squared. So there's not really much we can do on that. Let's plug in the second answer choice. I think you'll see something cool here. So we have from 2 to, this case, x equals 1, right? So we have 2 times 1. And lo and behold, 2 times 1 is 2. So anytime you have an integral of whatever the function is, if you're evaluating it at the same points, it just equals big fat 0. So if you plug in that, this tail end becomes 0, so it is equal to 5. So a bit of a tricky one there. But the key was to not give up on it, and notice that you can use a second fundamental theorem of calculus to eliminate 3 of the answers, and then, you know, from here, 50-50 shot's pretty good. Okay, let me erase my notes here. You can see that we have a slope field, and we have our differential equation. So, you know, really we could solve this and see kind of what's happening, and then maybe we could see a shape in our head. So we notice that if we cross multiply, we don't have to take natural log or anything like that. So we have y dy equals x dx. So that's y squared over 2 equals x squared over 2 plus any constant, right? Well, if you multiply this whole thing by 2, you would get y squared equals x squared plus 2 times a constant, so it's still a constant, right? And if you take the square root, you get plus or minus, right? Plus or minus x squared plus the constant. So that might be helpful to look at. Looks like this slope field creates circles, right? So we're probably going to eliminate that one. You know, maybe another way to look at it is to go in here and look at some of the simple things over here. Like, I like to use what I call quadrant analysis. Since x and y are both positive, in the first quadrant all of my slopes need to be positive. And also, over in quadrant number 3, the x and y coordinates are both negative, right? Negative and negative. So the slopes have to be positive here. So just looking at this one is positive, right? This one's positive, so it could possibly be this one, right? But over here, the x value is negative, and the y value is positive, so all of my slopes have to be negative, and I can see that there's some positive slopes in here, right? See there and there? So I'm going to eliminate A right off the bat. And looking at this one, I see negative slopes here right away, so I'm just going to eliminate that one. I see positive slopes here, and I see some negative slopes. Oh, well, no, I still see positive slopes here, right? Yeah. But here, I have negative slopes here, and negative slopes here, so maybe I'm not going to rule that one out just yet. This one, I have negative slopes here, so definitely going to cross that one out again. And So it's between C and E. Let's look at E. Here, if I go over to 5 and 5, my slope should be 1, right? And if I go to 4 and 4, somewhere in here the slopes are 1. And you can kind of see that there's a straight line here, right? And it goes all the way down here. So, and then likewise, you can look over here and see that you have sort of a negative 1. So every time the x value at 2, you go up to positive 2, and the slope should be 1. If you go over here to 2 and down to negative 2, it's 1. And if you go up here to negative 2 and positive 2, you should have a negative 1 slope. So that's probably the easiest way to look at this one. So really, you just have to get a little practice with those. Okay, and this is number 17 on the calculator section I left off. So I'll go ahead and do it now. It's showing us that the graph of the function is shown. Let me see if I can make that a little bit bigger. Okay. So the limit as x approaches b exists, and f is not continuous at b. Okay, so, you know, the limit exists, but it's not continuous. That means the limit from the left has to equal the limit from the right. But the function value is not. Function value b is not equal to the limit. So I guess we have to start looking at some of these points. Here, the limit exists, but the function value is circled in, so that's not 1, because we could just start eliminating them. At negative 1, the limit's negative infinity and positive infinity, so we can eliminate that one. At 0, the limit approaches 2 from the left, it approaches 2 from the right, but the value is, the function value is, say, a 1.5. So it looks like that's probably the answer, huh? Now you can verify it at 2, there is no limit. From the left doesn't match the right. And at 3, the limit is here, and the function value is also the same. So we can eliminate 2 and 3. So, alright, that was kind of a long video. Go to the College Board and take a look at the test, and it should be helpful.